Guys, look at my bill.
Why? What's the problem?
My electricity bill is so high. What should we do?
I don't know. Just don't use your electricity every day.
Got it. How about if we have an energy storage facility using renewable energy?
Yo, Peter has a great idea. We would save so much energy.
We are Hydrogonia Consultants. Our firm consists of hydraulic, geotechnical, and environmental engineers. We will be proposing the construction of a storage energy facility complete with a secondary upper reservoir near the San Vicente Reservoir in Lakeside, California. Water will flow between two reservoirs via a reversible pump turbine system to generate 500 megawatts of power during peak hours for the surrounding regions. Water will flow from the upper reservoir to the lower reservoir, which will allow for the turbine to spin in order to generate power during peak energy demand. During off-peak period, the turbine will switch directions and pump from the San Vicente Reservoir back to the upper reservoir.
Initially, screenings for each site were performed and 4 prospective sites were chosen. The key factors that affected site decisions are specific geological and topographic conditions that would allow reservoir construction, appropriate and optimum head, amount of storage available, overall estimated costs, community impacts and public concerns, site access and land acquisition, and meets the energy demand criteria. Our strategy for choosing a location for the upper reservoir was looking at a topographic map and focusing on valleys. Once the initial screening phase was completed, the project team verified 4 potential sites that would meet the client's requirements and can produce 500 megawatts for 8 hours as the desired power. Site 1 was chosen in this valley close to Iron Mountain due to the high elevation in the surrounding area and the availability of a valley. Site 2 is located nearby valley northwest of the San Vicente Reservoir. By following the contour lines of the valley, it prevents the need to create a man-made lake. For Site 3 is located northwest of the San Vicente Reservoir and northeast of Foster Canyon. The contour lines will be taken advantage of as much as possible in the design, but 5 embankments will need to be constructed on the lower ends of the perimeter for the design to work. And lastly, Site 4 is located northeast of the San Vicente Reservoir, north of Borona Valley. And Site 4 had the most significant elevation change.
According to the scope, it requires to create 500 megawatt in 8 hours a day. However, the 500 megawatt is not our goal to design. Due to the efficiency of reversible pump and turbine, which were studied by Black and Rich, is 77% and including other losses. We have to design the cost power amount of 650 megawatt. Once we figure out how much power we need, then we can start designing 4 proposed sites based on topographic map. After picking the sites, we can calculate how much volume each site needs to have by carefully looking at the elevation from the topo map. We follow the contour lines to shape the proposed sites so that the volume of the sites are adequate and sufficient to generate net power of 500 megawatt for 8 hours. After comparing the cost analysis, geotechnical analysis, and environmental impact from 4 sites, the Site 3 has been chosen. We need to go for more detail in terms of calculation to get all the related parameters. We finally come up with the flow rate is 11,000 cubic feet per second. The volume is 210 million cubic feet. The area is 89 acres. The depth is 80 feet.
The embankment for the preferred site was designed to be similar to the existing parameters of the current roller compacted concrete dam of San Vicente Reservoir. A crest width of 20 feet was maintained. A slope of 0.8 horizontal to 1.0 vertical was also used for the upstream reservoir. And the height at every interval within the dam was calculated at 40 feet contours. In order to determine how wide the embankment would be, different sections were taken at different elevations within the valley. The height of the embankment was determined at each specific station, and by using the given slope, the distance from the face of the dam was determined. Afterwards, at each specific section's volume was calculated in order to find the exact given volume for the embankment design. In order to calculate pipeline design, we needed pressure, allowable stress, pipe diameter, and pipe thickness. The thickness of the pipe was calculated at every 50-foot station, starting from the inlet outlet all the way up into the upstream reservoir. The thickness of the pipe along the alignment was reinforced with steel lining in order to protect the pipe network from internal and external pressures.
While this project is primarily hydraulic, we still have to take into consideration the soil types in the area, as we're going to be doing some tunneling and we're going to have to know what we're dealing with. Now, based on our research, we found out that around the reservoir, the soil is composed primarily of clay and fine-grained soils. And underneath that, we have some metavolcanic rock. The estimates you see in the slide are in feet, and they are rough estimates. Now, there are some hazards and considerations for this particular project when it comes to geotech. There is a prevalent issue of seismicity because there are 3 fault lines nearby: the La Nacion Fault, the Rose Canyon Fault, and the Elsinore Fault. With the earthquake hazards, there's also the problem of liquefaction, which would damage the underground structures and possibly our foundations for the embankments. Soil in the area has high erodibility, which means over time the foundations could get weaker. As for landslide hazards, there aren't any currently, but because of the nature of the soil, that can change if the land is modified. We're attempting to address that by, in our design, we're going to keep the design as close to the natural contours of the land as possible, as you will see in our site drawings. With all of these in mind, regardless of how the facility is constructed, we're always going to have a risk of earthquakes. So we're going to have to be able to build the structures with that in mind and to be able to withstand tremors. And as mentioned before, we're going to try to impact the landscape as minimally as possible, so erodibility and landslides won't be as much of an issue.
In order to ensure that this project remains environmental friendly, an environmental impact report was conducted. 4 sites for the upper reservoir were analyzed. The main impacts focused on aesthetic and visual, air, biological resources, geology and soils, and finally water resources impacts. Being the farthest from the current location, site number 1 was discovered to have the greatest biological impacts of all. It was also discovered that this area provides habitat to a sensitive plant species named the Engelmann's oak. Site number 2, after conducting a biological analysis, it was discovered that it provides a habitat to major species populations, which include native and non-native plant species, and an estimated of 168 species of amphibians, reptiles, and mammals. Site number 4 required the biggest excavation of all alternatives, which as a result will have the greatest impacts on mineral composition, which could potentially weaken the quality of the surrounding rock. As you can see on the map, site number 3 is the closest to the existing lower reservoir and dam. This results in having the shortest pipeline and tunnel system to the powerhouse, which consequently has lower construction footprints and environmental impacts in comparison to the other alternatives. This project was determined to not have any effects on biological resources due to the fact that it didn't threaten any native plant species or sensitive major species.